Hi, I'm Matthias Bernert, working for the Max Planck Institute for Plasma Physics in Garching in Germany. Usually I'm working on a smaller device called ASTEX Upgrade, which is like JET, a tokamak. And here we also did already some developments, which we actually now want to bring to a bigger device, see how relevant this will be for a future reactor. So at JET, we are actually tackling one of the big challenges for a future fusion reactor. So usually the power which is injected into the machine arrives down in the divertor in a very narrow region. And usually there's no material which can withstand such high heat loads. Now what we are trying is to distribute this directed heat load all over the surface of the tokamak, which then makes it much easier to handle with that, and with which we can also later on produce much more power. So what we are trying to do is we inject impurities into the plasma, and these impurities then radiate away the energy in all directions. And with this, we by now also manage to reduce the heat loads down to the divertor region to an insignificant level. So in the experiments and our smaller devices like ASTEX Upgrade, we observed that if we inject these impurities, the main radiation concentrates in a small region just above the X point. So the X point is down at the bottom of the machine, where we get these divertor legs. And with sufficient injection of these impurities, we can create a radiator which then sits there above this X point and moves inside the plasma. And in this state, we see that this is how we achieve the highest power dissipation, and by this can protect the wall. What we observed in ASTEX Upgrade is that we can actually have a control of where this radiator is, and by this move it up or down. And now we also want to try to, first of all, establish such a scenario also in the JET tokamak, and then later on also see if we can control such a radiator in its location inside the plasma, and with this stabilize this highly radiative scenarios, which otherwise would be very close to machine limits.
My name is Bernhard Sieglin. I work at the Max Planck Institute for Plasma Physics in Garching. For the last 1.5 years, I've been research topic coordinator within the EUROfusion framework. And within this topic, I had to coordinate the development of the control capabilities on the different devices, and now especially JET. The main focus point is that in the end, we want to build a reactor that produces energy. And of course, you have to understand the physics to build it, but you need control to be able to operate it in the end on a 24/7 basis to provide energy. And there you need to control because, like for example, in a plane, it doesn't automatically work, but you need actuators to keep the plasma in the state where you want to have it. You need in principle 3 components. You need to be able to measure where this radiating region is. You need a control logic that can tell you what action should we do to keep it there. And you need an actuator that can ensure that the radiating region is doing what you want it to do. The beauty of this is that when you want to develop a controller and you apply it to the plasma in our case, you immediately see if it works or not. You don't need a big analysis to tell you exactly the nitty-gritty details, but you know where you want your plasma to be, and when you apply it, you see whether it is there or not. The difficulty is, of course, to get the logic to develop the controller so that you have a positive outcome. We started with this actually in the last campaign. So we implemented all the observers to detect this radiating region. We did first experiments where we applied system identification. This is a method to see how the system is responding, and from that you can then develop the controller to in our case, control the gas valves to keep the plasma in the desired state. And we did this already in the previous campaign, because you cannot do this within a couple of days. You need a lot of preparation. There is a big team working for this. And of course, this needs some lead time. And in the last campaign, we did this in pure deuterium to validate that everything is working. We demonstrated that the detachment control is working. And now in the deuterium-tritium experiments, we redid the system identification to check if there are any differences between the pure deuterium operation and deuterium-tritium operation, and then developed the controller and applied them to deuterium-tritium plasmas and demonstrated that the detachment control is also working there. We have to focus where we want to be. In the end, we want to apply the same on ITER. ITER will be a larger device, but it will also run with deuterium-tritium. JET is so far the only machine which we currently have that can run in DT. So trying it there is the obvious choice. Since JET will close at the end of the year, now is the time to do it, because we cannot do it later, because the machine will be closed. And of course, these experiments, they are conducted also on other machines. For example, on ASTIX Upgrade, we do the same experiments. Other machines do them as well. And there is modeling going on for these experiments, all in the aim that we know really, does this work on ITER? And what do we have to do to make it work on ITER? And therefore, it's really important to get the step ladder out, and there JET is really a vital part.
To do this, we first started to look into, in the deuterium campaign, does this regime exist? So we injected these impurities, and very early on, we could see that this radiation also comes up at a JET-like tokamak. So this is already very promising to us, that we see a bigger device can reproduce such a regime. And therefore, we are also quite positive to look for a future reactor to work in a similar operational mode. Now, the way to get to there can be quite cumbersome. So we invested many discharges, quite some days and weeks at the JET tokamak to first develop the scenario, then stabilize it, and also gain more and more experience. And with the higher experience which we gain, we also learned what are the parameters with how we can control this regime. And so not only in the deuterium campaign, but also in the DT campaign, which is much more reactor relevant, we then could also initiate such a control. And we saw in the end that going from our small devices to a bigger device, the control actually even gets better. So we have a much finer sensitivity of this radiator. We can move it up into the plasma, we can move it down. We are always in a safe and stable operation, while during all the time, there's no heat load going down to the divertor. So this was, for us, a big positive surprise that this works quite good. Usually you would think going to a bigger machine, everything becomes more difficult. And indeed, there are some difficult steps on the way. But the scenario which we developed and which we could later apply with this active control proved that this is a very sturdy regime. And therefore, we are now really looking forward to make more detailed calculations, how to get this how to make this possible in a future reactor.
What we actually learned from the smaller tokamaks, but also going to JET, is that especially this X-point radiation seems to be a very universal feature of tokamaks per se. And if we can really apply that also for a later reactor, this would mean we have a quite easy solution for this so-called challenge of power exhaust. So, there are many other means how one tries to overcome that. But actually with the X-point radiation, we would have a very easy access to get to that at actually quite limited costs. And if you even think about this further, this could also influence how you design a future reactor, because it simplifies actually some of the ways to go to, and might in some ways also then allow to have future reactors a little bit cheaper in construction.